So what I would like to talk a little bit more about is the community part of the Valkey project. So Quasi gave a little bit of a tidbit of, Redis used to be, kind of the de facto open source cache. And then they, very publicly fired me and dissolved, they fired another core maintainer of Valkey as well at the time, an engineer from Alibaba named Zhao. And so, the group came together and we had to go and create a fork, which became Valkey. And initially the point of Valkey was just, hey, we're open source Redis. But that's not a really exciting mission. Nobody just wants to be an open source version of something else. And so one of the missions we really sort of consolidated around is we just really wanted to be like Redis, but just foundationally a little bit better. We wanted to be faster. We wanted to be more performance. We wanted to use less memory efficiency. And all of that without causing any degradations. One of the very early conversations I had with a user was like, well, we'll happily move to Valkey is if you can just promise that the code will stay the same 5 years from now and won't break. That's all they cared about. They didn't really necessarily need new features. They would love if there was new features, but they really just wanted to keep everything together. So what I want to talk about in this session is sort of how we as a community think, and some of this is just my opinion, but I know others think this as well, about how do we make Valkey better without causing regressions. So I'll kind of go over some guiding principles, and I also want to kind of sprinkle through all of the unique contributions from different members of the community, and why I think Valkey is better positioned to be a fast-moving, innovative project because it's a vendor-neutral project, it's community-driven. There are currently 9 members of the technical steering committee across 6 companies, which I think is what makes Valkey so great. So I am going to start the story at Redis just because I think it makes a nice timeline. So the way I think about performance in Redis is in a much smaller time scale than most people think of. So there's a blue line at the bottom of the screen, and I want you to imagine that's about 10 microseconds. So when people think about 1 million requests per second, that means we're doing 1 request about every microsecond. So we'd be able to do about 10 requests in this time frame. And at this time frame, things can take a long time. So even if there's no requests coming in, periodically there's going to be cron jobs happening, both in Redis and Valkey, and those can take a couple of microseconds. And in the worst case, they can take tens or hundreds. And so we do care about how long individual small jobs take, even at a very small time frame. So let's move forward and let's add some load to the server and see what Redis is doing in this small 10 microsecond time frame. So when a request come in to Redis, we have to read the request off the network. We have to process the TCP packets. Might have to do some TLS decoding. Then once we have the command, we have to parse it. It's not just a raw TCP packets. We have to then go look up that request inside the main hash table. We have to get the value out and then write it back out to the connection. And, kind of back in 2016, 2017, this took, somewhere between 5 to 6 microseconds. So, right, a good chunk of time in our world. But obviously the latency is extremely low for most end users. They're not noticing, they're seeing requests come back very fast. But what happens if we send 2 requests at the same time? So Redis is notoriously single-threaded for good and bad reasons. But when 2 requests come at the same time, we process them serially. So in this case, we'll process foo first, then we'll do get eclipse, and then maybe we also have some cron jobs going on that's going to take some more time as well. So we've kind of almost fully saturated our 10 microsecond slot of time, but the end user is not noticing any latency spikes. And that's because this is all happening so quickly that the end user won't notice anything, right? Within 10 microseconds, we've already flushed all the data out to all the buffers, and most end users' applications won't notice sub-millisecond time periods because Redis and Valkey are mostly used as a remote cache. So the real time is going to be bottlenecked by network transit time. Even if you do stuff like placement groups, you're still seeing 50, 60 minimum microseconds of time to go to another server. When we really start seeing issues is when we're actually sending more requests than we can get done in these short time frames. So kind of once you start hitting 2 or 3 requests per second or within this 10 microsecond time zone, we're starting to see a lot of queuing happening. And this is what really causes latency spikes inside Redis and Valkey. is when you're doing too much work in a very small period of time. Your system might only be sending 10,000 requests per second, but if those 10,000 requests are in a very short time frame, you're going to see very, very high latency. So this is why, sometimes we call these microbursts. And this was sort of like the main problem that was sort of plaguing Redis, in the 2016, 2017 timeframe. And the solution that at the time the project came up with was to do horizontal scaling. So instead of having one server, you're going to split the load across multiple different servers. And this is a great strategy. You get basically linear scaling for the same amount of actual underlying hardware. But it doesn't solve a couple of important problems. One is that it doesn't solve hotkeys, which for caching is extremely important, right? You often have, Taylor Swift, when she publishes a tweet, everyone's going to go be opening that tweet. And, all of the requests are going to be sent to the exact same node. And we're going to have the same problem we just talked about, which is these latency spikes, because we're hitting one specific shard with too many requests per second. Another problem is also not all workloads support cluster mode very well. Cluster mode requires a very specific sharding technique. Basically, the name of the key is what gets mapped to the slot that Kwaja talked about earlier. And if you want to have data basically be processed atomically and together, you have to basically force it onto the same slot. So some workloads just don't scale particularly well in that case. So it's a good strategy. I love cluster mode, but it doesn't solve all of the problems. And so, I talked a little bit. I officially work for Amazon Elasticache. I'm also, work primarily on open source Valkey. But we saw this problem inside Elasticache, and we tried to fix it. Right? We launched this feature, which we called Enhanced I/O, which basically offloads some of the work off the main thread that we're seeing being the contentious points, and we offloaded it to other threads. And we actually pushed very hard at the time to try to do something in open source. We talked about open source area implementation, but we didn't see a lot of interest from the community. And a lot of this is because Redis's goal was to be very simple. Redis didn't like adding a lot of complexity, which is great for maintenance, but it's not necessarily in the best interest of all of the end users of the application. But, after we launched this, Redis was a little bit more interested in building I/O threading. So, as I mentioned, if you actually go and look at how much time is spent processing a simple command, what you'll observe is most of the time is actually spent in I/O. So a huge chunk, about 30%, is spent doing the reading in of commands off the network. There's a very small sliver of time that's spent actually processing the commands. And then there is another chunk of time spent actually writing the data out. And now what's really nice is I/O is actually very parallelizable. The reason that Redis wanted to keep the main thread simple was because they didn't want to have contention and locking for all the command execution pathways. So Redis came up with a very simple solution, which is we'll have two phases of execution. We'll have a phase where we're doing I/O, and then we'll have a phase where we're doing command processing. So this was sort of their, poor man's attempt to build better multi-threading. And it does solve the problems we're talking about, right? We're seeing less queuing, less contention. But any engineer that looks at this is going to be very unsatisfied because it's not really utilizing the underlying threads and cores very well, right? If we assume that we're pinning each of these threads to one core is idle a bunch of time during I/O because there's not enough I/O for it to process. And then the other thread is completely idle during command processing because it has nothing to do. So as it starts scaling, you get more throughput. You start running into Amdahl's law problems of, you're eventually going to be bottlenecked on how much time it takes to actually execute all these underlying commands. So this was the state of the world when the fork happened, right? When Valkey was created from Redis. And we were actually really excited about trying to improve this. So there's a kind of a period of time after there was previously a single threaded owner of Redis. He passed off to a core group, which I was a part of. And in 2022, we were like, hey, we should really make this better. And we knew there was a lot of problems. We just talked about some of the problems. But we really couldn't get any consensus to make this happen. If you go and look at this issue, it's very boring. There's not that many comments on it because we kept having these secret core meetings where we talked about making I/O threading better. And we kept getting a stonewall, no, we're not going to do anything about it. So even though two of the maintainers, me and Zhao, the guy from Alibaba I mentioned earlier, really wanted to make this better, we were basically stonewalled by Redis and said, no, we're not going to fix this. So just looking at timelines, so this issue was open in 2022. The second issue, the one where we're like, hey, here's a concrete implementation of how we can make Redis's I/O threading more performance in 2023. This is 4 years after Elasticache announced it. It was built on technology we built inside Elasticache. This PR was still never merged. We never got any traction on this. If you go, it's 12.489. You'll see there was one response from Oren, one of the other maintainers. He was like, this is complicated. We don't want to do this. And that's really disappointing, right? There's a lot of rocket ships. People were very excited. But there was no traction, right? Because we weren't able to convince Redis that, like, hey, this is important to do. We need to make progress. So this was sort of the stage of like when we forked from Redis, right? This is when the license change happened. This is when me and the other engineers got fired, and we started the Valkey project. And as I said earlier, like we really wanted to make improvements. Like we saw these problems from our users. We wanted to do multi-threading so we could improve this contention issue for those edge cases, those microburst cases. And so we were very enthusiastic about doing stuff. And it came out inside, one of the very first issues that got ported over to Valkey, number 22, was basically one of the maintainers saying, hey, let's go revive this, right? And just so everyone's on the same page timeline-wise, March 24th, that's a full year after the issue was opened, so there had been no progress on the issue. But we were excited to keep going and keep trying again. And so we were actually able to merge this. And it actually merged fairly quickly. I think it got merged in July of 2024. So one of the very first features we built inside Valkey was an improvement to the way the I/O threading was working, right? So this was something contributed by AWS, something we had built a lot of expertise in. And the theory was very simple. It would look basically the same, except instead of having two discrete phases, we just let I/O run in parallel. And this is abstracting away a lot of the detail. There's some other good talks if you're interested about how this works. If you're interested, there's some blogs that go into a lot of detail about how we did lockless queues to basically send messages between the different threads to get good performance. And we were able to kind of prove like, hey, this actually isn't all that complicated. And the overall amount of time being spent is quite a bit less. But one of the other things that was very exciting about this I/O threading work was that we observed that when threads were parsing the commands, and then they actually went to go execute on the main thread, they were taking longer than they would have on the main thread. And that's because although the command was being processed on the I/O threads, that CPU had in its CPU memory caches, like the parsed information, but we actually need that parsed information on the main thread, right? Because that's the one actually executing commands. It needs the one to actually dereference the data. And that was an innovation that was brought by a new engineer. He wasn't there when we originally built Enhanced I/O. And it really shows that bringing more diversity of opinion matters for improving work. And so what we observed is, in certain situations, we actually got better performance. Like commands were actually taking less time with the I/O threading implementation, like in net less time, because we were able to basically better groom the underlying memory layout. And so, overall, we're able to do even more commands in sort of the same amount of time, which again is great for, we are able to, reduce contention, reduce P99 latency, which Quadra talked a lot about, very important. Because even on these very small time frames, we're able to execute even more work. And what I love about this is that, another engineer observes something else, which is, okay, we're doing all this memory prefetching. We don't need to be using I/O threads to be doing this prefetching work. And this was the work that, Quadra talked a little bit that we launched in 9.0. And an engineer was like, hey, why don't we just do all the I/O, then do all this memory prefetching, and then go execute commands, which on the exact same hardware that we were a few years ago, we're able to execute even more commands than we were before. So at the very beginning, we showed, hey, we were only able to do about 3 commands, and now we're able to do 3, but we're able to hit our time constraints. We're able to not see contention, so we're not seeing any latency spikes. And this was something that Ericsson contributed, and it was because they extensively use pipelining clients, and they were like, we want to see better performance. We don't want to use this I/O threading stuff. It's complicated. It breaks our architecture a little bit. We just want to make the actual work better. And that's something I don't think we would have naturally observed. Inside AWS, we had a bunch of performance benchmarking that only checked pipeline depth of 1 and a lot of I/O threads. And it wasn't until someone else was like, hey, we have a different workload. We need to do something else. That we really thought this through and were able to come up with a better solution. And I want to give a little bit of a sneak peek about, this is a little bit of a complicated slide, but kind of what we're working on. Because there's still one problem, which is that if a single command is taking a long time, the main thread still might get bogged down, and you're still going to see those latency spikes. And so we want to fix that. We don't want to do that. So we actually have ongoing work to go and offload read commands as well off the main threads. So this is a little bit more caveated than I explained, and it's not all merged yet, but I think it will be merged soon. And the core idea is that, especially in cluster mode, slots are basically an atomic unit, right? We execute commands against a slot. So as long as commands are targeted towards different slots, we're able to basically fan those all out pretty safely without having to run into any contention. So there's still a little bit of work happening on the main thread to make sure everything coalesces together. But we're very close to getting 2.8, 2.9 million requests per second on a single process, which we're all really excited about. And so this performance journey, we started around 250,000 requests per second with a single core, without I/O threading. And we're talking about getting to up to 2.5, 3 million requests per second. There's a really exciting journey there, and that all happened within about 2 years, right? So Valkey was formed in March of 2024, and we're in January, we're at about 22 months. A lot has happened, and I think a lot of this has happened because of the excitement and engagement of the community. So I've been talking a lot about just raw throughput performance improvements. So I want to talk about something else a little bit, which is we also care a lot about horizontal scaling. So Jacob's going to talk a lot more about in the future. But one of the things that's really important about horizontal scaling is we want to be able to take a workload and be able to dramatically scale it up and scale it down so you're not over-provisioning, right? So in the same way you want to best utilize the hardware you have, you also want to be able to efficiently not have to over-provision, right? It's still a performance goal for us. And so we both took aspect of trying to make scaling faster. The existing previous atomic submigration was very slow. What Jacob built and contributed by GCP helped make it significantly faster. And one of the other things that we'll also hear later talk about is how we got to 1 billion RPS. One of the main ideas behind there is we were seeing a lot of latency spikes coming from cron jobs, right? There's a lot of background work that was happening that was taking a lot of time that was proportional to the cluster size. So one of the things that both Tencent and AWS contributed to was making those cron jobs more efficient and also basically improving the failover time so that we were able to restabilize more quickly. So when we think about performance, we're thinking about kind of a whole host of areas. We want to, primarily we want to maximize throughput efficiency. We want to take the hardware we have and we want to make sure that we're using it as efficiently as we possibly can. So we got this through features like the pipelining we talked about. Kwajal also mentioned a little bit of a feature called copy avoidance, which was that in earlier versions of Valkey, the way we handled sending a request out to end clients was we basically copied it into an intermediary buffer and then out to end clients. We now no longer do that when the request is large enough. So if you're trying to read out a 10 kilobyte object, we'll just keep a reference to it and then directly write it out either on the main thread or on an I/O thread, depending on the configuration. And also little stuff like trying to optimize these underlying cron jobs that are taking a lot of time. Another important principle is we want to make sure that we provide very predictable end user latency. So we're getting this through making sure that nothing is taking too much time inside the Valkey engine, right? We want to make sure we're being fair in how we're splitting out requests. Also, these cron jobs, it's also important to make sure they are not taking too much time because that can cause unpredictable latency spikes for end users. Recently, another one of the engineers here, Jim Brunner, built an improvement to the active defragmentation system. Before, there was basically large spikes in how much time it spent basically reallocating and defragmenting memory. And he made sure that was just bounded so that end users saw predictable latency. So all of these are very important to get the latency characteristics we're looking for. And then additionally, we talked a little bit about supporting fast scaling. So I talked specifically about atomic slot migration as a way to scale out horizontally more quickly, but there's also stuff we want to make BG safe faster. One of the early features we built in Valkey 8.0 was a dual channel replication feature, which basically doubled the speed at which we could do vertical scaling from one host to another, which is great when a node fails, or you want to do upgrading, or you want to add replicas to better support read throughput. So being able to scale very quickly makes it easier to use less hardware initially, because then you can trust that you can add more hardware as needed. What's interesting is this is one of the big contributing factors of why Elasticache also wanted to open source our IO threading implementation, is because we were using it to basically scale our managed offering more quickly, and we didn't want to have a custom implementation for it. And I talked earlier that one of the goals of Redis was to keep everything very simple. But I think they tried to keep things simple at the cost of the other three, right? They didn't care too much to maximize throughput or provide latency or do fast scaling. The goal was really just to keep the underlying architecture very simple. And so although the Valkey community cares a lot about keeping things very simple, it's not at the cost of the other three. And then just to kind of recap everything out, the other extremely important thing was we didn't want to regress on any performance anywhere. Redis sort of got this implicitly because they tried to keep everything simple. They never did anything. So if you don't do anything, you can't regress on anything. And so we had to actually spend a lot more work to make sure that the Valkey project was not regressing. And so we've been doing a lot of stuff. Quadra talked a little bit about improving benchmarks. We also recently started producing a automated benchmarking tool. So if you want to go to valkey.io/performance, you can see basically the latest numbers of performance based on each version. So this isn't necessarily a super representative set. These are for get commands with varying numbers of IO threads and pipeline depth. These are like our 4 key workloads, right? So 512-byte objects with and without IO threading, and then with and without pipelining. And you can kind of see here in the graphs that we have some very clear examples of when we saw performance improvements. So the green one is, far left one is Valkey 7.2, or the last open source version of Redis as well. We can see the big spike up when we did the IO threading work. And then we can also see the 2 instances of us also doing the reply offloading work as well as the pipelining performance. And I talked a little bit about, there was an engineer at Ericsson that said, hey, we should also make pipelining better. One of the reasons that this conversation came up is we realized that with pipelining and IO threads, the performance was worse than without pipelining. And all of our guidance online was like, you should use pipelining. It makes performance better. So the fact that we found a place where it was worse was like, OK, that's probably some area we need to work on. And the other really cool thing about this technology that we built, and we're still working on, and so if anyone wants to contribute to it, we'd love to help, is that we've built automatic monitoring for every commit that goes in. So this is a commit that came in recently. So the workload was the pipeline depth of 1 with 9 IO threads. And so basically the bar is like the throughput. So it's all within 1%. I'm just curious, how many people think that this might have been a performance regression? Nobody? Because it actually was, because we weren't testing the right workload. One of the things we realized was that we were actually missing some cases, and this tooling actually caught it. It basically showed, hey, that if you have very high pipeline depth, so this is the pipeline depth of 10 with IO threads, we saw a very sharp, about 15% performance degradation, and that we need to go fix it. We haven't launched this yet. This is part of the Valkey 9.1 payload. It's actually a very cool feature. It's memory efficiency improvements. For very small key values, we're able to remove about 8 bytes of overhead, which doesn't sound like a lot, but is about 20-ish% of the overhead. So if you have very small key values, you'll see less memory usage in Valkey 9.1. But one of our key tenets is we don't want to regress on performance. So we've identified this, and we're going and investigating sort of what happened here. And we think it's related to memory prefetching and how we didn't quite groom the memory layout of a CPU correctly. So we're looking into it. But this type of tooling makes it much easier for us to make sure we don't have regressions. And there's a link at the bottom. You can go explore around, see all the commits and what's going on. So I've talked a little bit about what's coming next for Valkey kind of throughout this talk, but I wanted to reiterate them, specifically in what we're doing for performance. We talked about read command offloading. This is the 3 million RPS feature we sometimes talk about. And this allows us to do read commands in parallel. I've talked a little bit about how great it is. It also helps a little bit if you have very expensive read commands, it's going to improve your throughput a lot. The 3 million RPS is sort of with small gets commands, but we've seen some workloads that we've tested against where we've seen like 5, 6, 10x improvements because we're fully offloading all of the read work onto IO threads. So we'll make a blog about that. We'll talk more about it soon. Quadra also talked a little bit about the new multiplexing protocol. This has come under a couple of different names. It's the REST-B, the binary REST protocol. There's been some conversations that maybe we should split out something for the protocol specific for the proxies, which Quadra loves, and I don't care so much about. Another really thing is, we talked about fast scaling. One of the huge pain points we see all the time with our fork-based approach is we see very high copy on write when you're using a high write rate application, right? Doing something like rate limiting, you're sending a lot of write requests, which causes a lot of copy on writes, which uses a lot of memory on the primary. So we're also working on trying to improve a forkless implementation of replication to reduce that memory, and it can also be faster in certain circumstances. This is the first time interjecting is for multiplexing. You said he was going to sass me this whole time. He said nothing. Just sit there patiently.
Oh, the multiplexing was much more useful than just for the proxy. It opens up a lot of other things, like being able to deal with misses and getting it from S3 Express or SSD without blocking the rest of the commands on that particular connection and so forth as well. So I'm just really excited about the building block here of multiplexing protocol.
Yeah, multiplexing is really exciting. Yeah, the head of line blocking is really important. We've heard about it from a lot of users. You talked about it a little bit, so I was going to go into too much detail. Quadra and I theoretically had one talk, but we didn't coordinate at all. We just showed up together. We're two independent threads doing our own work. So hopefully it's coherent. But performance is through and through everything that Valkey is currently working on. So I also want to talk about a little bit about some other stuff that we're working on that we do care a lot about performance as well. I talked a little bit about memory efficiency. We have a commit inside Valkey right now for Valkey 9.1, which will improve memory efficiency by 20%. We're also spending a lot of time to try to figure out improvements to sorted sets, something we'd like to do for 9.1, but it's feeling a little bit of a stretch goal at this point, given how close the code cutoff is, but we're working on it. Because we see a lot of people use sorted sets for leaderboards, rate limiting, all sorts of stuff, and they use a lot of memory. They're the only semi-ordered structure that you can do arbitrary inserts and deletes in, so it takes a lot of memory to sort of keep track of that. We're not doing a talk here, but we'll do a talk pretty soon, I'm sure, about full text search capabilities. So there's a module called Valkey Search, which enables you to do vector similarity search. The first time, I guess, we're going to mention AI at this conference, and hopefully the last. At some point, I'm going to stop making that joke, but people laugh every time. So it's a fun time to be alive. So full text search is important. It lets you do hybrid search, which is important for semantic search used in agents and other types of AI workloads. But also full text search is powerful for building real-time commerce. And this is a really important thing to be very performant on. A lot of engineers are spending a lot of time building a really performant full text search feature. And I also include Valkey admin on here. The complete complement to performance is observability. You need to know when something goes slow, what's happening, why is it slow. So we're putting a lot of effort in making sure the Valkey admin, which is basically a GUI in front of Valkey, making sure it's good. It's just a GUI. It's a very fancy GUI. It's more than a GUI. It does, but you can have an intelligent GUI. I'm sorry, this is why we need the CMO of Valkey to hype things up a little bit more. I'm just an engineer. And to close out, I have 15 minutes. Okay. So I just want to close out. Like, there's still a lot of excitement going on. If you want to get involved and get invested, come talk to me. I asked everyone to raise their hands at the beginning about other people contributing. Go talk to them. I'm really excited you guys are all here. I'm really excited for all the talks. Hopefully I set up some foundations for what's to come about, how important performance is, how all the stuff is we're working on. So I'm actually done. But thanks for being here, and yeah.